Hi, adding up infinitely many numbers, does it make sense? Or in mathematical terms, if you have a series, does it converge? In other words, does the sequence of partial sums have a limit? If you are lucky, you can simplify the partial sums and find an easy formula for them. For example, if you have a geometric series, there's a nice formula for the partial sum Sn that enables us to see if the partial sums converge, and if they do, find the limit. But what if there is no easy formula for the partial sums? For example, consider the sum of 1 over n squared with n from 1 to infinity. Let's look at the sum of its partial sums. S1 is simply equal to the first term, which is 1. S2 is equal to 1 plus 1 over 4 is 5 over 4 is 1.25. S3 is equal to 1 plus 1 over 4 plus 1 over 9 is 49 over 36, which is approximately 1.361. S4 is equal to 1 plus 1 over 4 plus 1 over 9 plus 1 over 16 is 205 over 144, which is approximately 1.424. We could go on like this, but there doesn't seem to be an easy formula for these partial sums. We observe that they are increasing, which does not come as a surprise, since all terms are positive. So each time we add another term, the partial sum is greater than the one we had before. So the question is, what happens on the long run? There are two possibilities. The partial sums are either unbounded or bounded. If they're unbounded, they form an increasing sequence that exceeds all numbers, hence divergent. But if the partial sums are bounded, we are dealing with an increasing sequence that has an upper bound, and so the sequence must have a limit. So if that is the case, our series is convergent. Now let's have a closer look at our example. Here we see the first 4 partial sums, and their values are less than 2. But that does not guarantee that all the partial sums will be less than 2. Okay, the additional terms will be smaller all the time, but there are infinitely many of them. So who knows what will happen to the partial sums if we keep on adding terms? Let me show you a picture that will help us to get grips with this situation. Look at these rectangles in the xy plane. For convenience, I used different scalings for the 2 axes. The first rectangle, which happens to be a square, has width 1 and height 1. Hence its area, which is equal to A1. The second rectangle has width 1 and height 1 over 4. Hence its area is equal to A2. The third rectangle has width 1 and height 1 over 9. Hence its area is equal to A3, etc. The nth rectangle has width 1 and height 1 over n squared. Hence its area is equal to An. So, in our picture, the terms of our series are being visualized as areas of rectangles. And we want to know if the total area of all these infinitely many rectangles is finite. We add to our picture the graph of the function f of x is 1 over x squared, for x being greater than or equal to 1. Note that f of 1 is equal to the first term of our series. F of 2 is equal to the second term, etc. F of n is equal to the nth term of the series. Moreover, since f is a decreasing function, our rectangles, starting from the second one, are all completely between the graph of f and the x-axis. Roughly speaking, the area between the graph of f and the x-axis is equal to the improper integral of f for x from 1 to infinity, and you may want to verify that this integral is convergent. So the area under the graph of f is finite. Thus, we may expect that the total area of the rectangles, starting from the second one, is also finite, and by adding the area of the first rectangle, this would mean that the total area of our rectangles is finite. Now let's be more precise. The partial sum Sn is equal to A1 plus the sum of A2 up to An. In our picture, we can see that the sum of A2 up to A6 is less than the area under the graph of f from 1 to 6. This area is equal to the integral of f for x from 1 to 6, which is equal to 5 over 6, hence less than 1. Adding A1, which is equal to 1, we find that the partial sum S6 is less than 2. We can do this for all the partial sums. the sum of a2 up to an is less than the area under the graph of f from 1 to n, this area is equal to the integral of f for x from n to 1, which is equal to n minus 1 over n, hence less than 1. Adding a1, we find that the partial sum Sn is less than 2. But that is the answer to our question. Yes, indeed, the partial sums are bounded. So now we are sure that our series is convergent. This example illustrates the first part of what is called the integral test, which is stated as follows. Suppose we have a function f that is continuous, positive and decreasing on the interval from 1 to infinity, and numbers an such that the function of value of f at n is equal to an for n is 1, 2, 3, etc. If the improper integral of f is convergent, then the series that adds up the an is also convergent. But this is not the complete story. Let us look at another example. Consider the sum of 1 over the square root of n, with n from 1 to infinity. Now we could draw the same picture as before, this time with the function f of x is 1 over the square root of x. However, this picture is not very helpful, since the area under this graph is not finite. Indeed, the integral of this function with x from 1 to infinity is divergent. So the observation that the total area of the rectangles is less than a1 plus the area under the graph leaves us in uncertainty about the question whether or not our series is convergent. But the slight adaptation of our picture helps us out. Let's shift all the rectangles 1 unit to the right, while keeping the graph of f in place. Since f is decreasing, the area under the graph of f is now fully covered by the rectangles. So, roughly speaking, we may say that the total area of the rectangles is greater than the area under the graph, hence infinite. To be more precise, in our picture we see the partial sum S5, which is equal to the total area of the first 5 rectangles. It's greater than the area under the graph of f for x from 1 to 6, which is equal to 2 times root 6 minus 2. In the same way, the partial sum Sn is greater than the area under the graph of f for x from 1 to n plus 1, which is equal to 2 times root n plus 1 minus 2. This shows that for increasing n, the partial sums grow beyond each limit. So the sequence of partial sums is unbounded. So whether you like it or not, our series is divergent. Now this illustrates part 2 of the integral test. Suppose f is a continuous positive decreasing function on the interval from 1 to infinity, and let an be equal to f of n for n is 1, 2, 3, etc. If the integral of f is divergent, then the sum of an is also divergent. Combining the two parts, we now have the full version of the integral test. Suppose f is a continuous positive decreasing function on the interval from 1 to infinity, and let an be equal to f of n for n is 1, 2, 3, etc. Then the sum of an is convergent if and only if the integral of f is convergent. Of course, if you are dealing with a convergent series, you also want to know the sum of the series, or if you can't find its exact value, you want an approximation. In class, you will learn how to use integrals in order to find such approximations. So, see you in class.